Hi guys, so today we are going to talk about an algorithm called Fortuna. But before we get into that, let's just think about the world we live in. It's exploding with gazillions of data that are being generated, processed, and transmitted. It is even predicted that by 2020, every individual would produce 1.7 MB data every minute. So as a result of which, computer scientists are very busy finding ways to handle this ever-increasing bulk of data. However, with data processing and data analysis, data security is also of paramount importance. So, let's just say that brings us to the topic we are going to talk about today, which is Fortuna. It is a cryptographically secure pseudo-random number generator, and Hima and I, Sananda, are going to present it. Okay, then let's get started. So the contents are mainly Fortuna, what it is and why we need it, then what PRNG is and how that is useful or how that is being used. We're also going to look at the components of Fortuna, which are mainly accumulator, generator, and a seed manager. Then we will understand the algorithm behind it. We will look at some applications. We will also survey them and then look at the loopholes in the system, the prevention from them, and finally the summary. But before we dive into what Fortuna is right away, let's just try and understand what random number generators are. So they are very popular in modern cryptography. Practically every cryptographic protocol requires the use of random numbers. And like for example, we can consider generating a key stream used in one-time pads or stream ciphers. A pseudo-random bit stream of the same size as the message is used to encrypt or decrypt the message. Then random numbers are also used to generate digital signatures, keys for AES encryption, large primes for RS algorithm, and, and more things like that. So random number generators fall into three categories. The first one being true random generators, which produce random data based on unpredictable physical sources, such as electrical resistor noise or oscillator phase noise. The second category is pseudo-random number generators or PRNGs, which use a deterministic method to generate random numbers, employing a truly random seed to initialize the algorithm. The third category is cryptographically secure PRNGs or CSPRNGs, which are PRNGs which have been specially designed to be resilient to certain cryptographic attacks. Fortuna is one such algorithm, and we will dive straight into that right now. So Hema and I wanted to study an algorithm which is associated to cryptography and security. And although like algorithms like AES, RSA, DES are very popular, we wanted to look into something more unusual. So we came up with this random number generator algorithm called Fortuna. So since then I didn't know what Fortuna was, the first thing that used to come to my mind is, does it have anything to do with fortune cookies? Which is why I have put that GIF down there. So what is Fortuna? It is a pseudo-random number generator algorithm, and it was published by Ferguson and Schneier. It is an improvement of an existing pseudo-number generation algorithm called Yarrow, which is basically named after the Roman goddess of chance. The algorithm is specifically designed to be cryptographically secure from known attacks. So there are three parts in Fortuna which we are going to look at in way more detail, but I'll just briefly go over them for now. The first part is the accumulator, which collects and pools entropy from various sources and occasionally recedes the generator. What is the generator? The second step is the generator, which takes a fixed size seed and generates arbitrary amount of pseudo-random data. And the third step is the seed file manager. Basically, it is a file control that ensures that the PRNG can generate random data even when the computer has just booted. Alright, so now we have gone over what Fortuna is and we kind of have a brief idea of how it works. But what's more concerning is, why do we need it at all? I mean, what exactly am I trying to accomplish using Fortuna, which cannot be accomplished using any other cryptographically secure pseudo-random number generator? So to understand that, first we're going to go over what a CSPRNG or a cryptographically secure pseudo-random generator is and where is it actually applied. So to generate any key material, we need a random number generator. And CSPRNGs are cryptographically secure PRNGs, which are used by programmers in all fields building secure systems to create cryptographic keys, encrypt communications, and defend anonymity. Yet many are based on deterministic algorithms, which if are broken can reveal all the numbers and everything to the attacker. So that's not what we want. So generating a good random number is the most vital part of many cryptographic operations. And doing this is very, very challenging. So the measure for randomness is what is also known as entropy. The reason why we need to understand what entropy is and how a good randomness is useful, we were going to see that later on in this presentation. So for now, we know what entropy is and what CSPRNG is and where it is used. So just to summarize that, CSPRNGs are a vital component in security. A CSPRNG can stretch the available entropy over more bits and hence securing more randomness, which as we just saw is good for ensuring cryptographic security. And fortunately solves the problem of having to define entropy estimators by getting rid of them. And why is that a good thing? We are going to see that in a while. Okay, so this is more like a continuated summary of what CSPRNG is and how it's different from PRNGs. So it's a little bit slower than PRNG, which is why PRNGs are more widely used. However, CSPRNG helps accomplish more security. So this is kind of a free body diagram kind of thing of how a CSPRNG in general works, or which is also what Fortuna is based on. It has three steps like we discussed: the entropy accumulator, the generator, and seed file. As can be seen from the figure, the accumulator produces seeds, the seed file writes and updates the seeds, and the generator actually gives the random number, which is the output that we are interested to find. And the generator also keeps taking in a key every time and updates the key for the next iteration. All right, so now we kind of have a base of what a CSPRNG is and what Fortuna might look like. Now it's time to actually go into its skeleton and study each of its components in more detail. So the first component is the entropy accumulator. And so the steps that it follows in accumulating the entropy is basically gathering data from truly random data, which is being generated from various external entropy sources, then using it to seed and reseed the generator. And the algorithm for Fortuna allows 256 sources of entropy. This is based on the implementation that we referred for this presentation. So random events from the external sources are uniformly and cyclically distributed amongst 32 pools that can be seen up here, which could be n pools also, for all that matters, from P0, P1, and up to P32, as can be seen here. So once pool P0 has accumulated enough random data, the generator can be reseeded. And once the pool has been used in a reseed, it is then reset to 0 again. So that's how the accumulator works in a more cyclical fashion. And once the reseeding process is done, it just moves forward to the next step, which is the generator. So following the entropy accumulator stage, the next stage is the generator. The generator first takes in fixed size random seed from the entropy accumulator and produces arbitrarily long sequences of pseudo-random data. The generator consists of a block cipher in counter encryption mode, and this implementation, as was chosen by the paper that we had referred, used an AES 256 block cipher. The plain text is used as the input to the block cipher, which is simply a counter, and the 256-bit keys are the output from the accumulator. So since AES is a 128-bit block cipher, it generates 16 bytes of data at a time. Once it has generated this data, it generates two further blocks, which will be used as a new key the next time it is required to generate the data. So as can be seen from the figure below, it's fairly simple that it receives the seeds from the accumulator and then checks for a seed or a reseed and then feeds in a random key, which is using an AES 256 block cipher, and generates the pseudo-random data, which is basically the output of the generator phase. The next step is the seed file management. So following the generator stage, the last and the final step in the Fortuna algorithm is the seed file manager. So the seed file manager, when I first came across the term, it wasn't really clear to me, and which is why I have used this cute watermelon slice, because it was as abstract to me, whether what kind of seed are they talking about and how is it going to be used. But coming back to Fortuna, after the generator stage, upon initialization of Fortuna, a seed file provides a seed to the generator. So that's where the seed is used as an input. This initial seed allows the generator to produce random data even before enough entropy has been gathered, which is in the accumulator phase. The seed file is read at startup and a new seed is immediately generated and written to the file. So while Fortuna accumulates entropy, this data is used to create a better quality seed. So to summarize that, the first step of the seed file manager is to initialize the seed and then to generate random data, then generate and write them approximately every 10 minutes or so. And the target is basically to generate better quality seeds, just as to ensure we have as random data as we can possibly achieve. So now that we have gone over the three individual stages of Fortuna, accumulator, generator, and seed file manager, we are going to try and put them all in a place and try and figure out the flow of the whole thing, which is going to be done by my friend Hima.
The compression function uses SHA-256 hash function, and this helps to cope with the storage problem, thereby maintaining a constant pool size of 32. And here, reseeding is performed by hashing the specified entropy pools together, and they use 2 iterations of SHA-256. Now that you've seen in the previous slides the components of Fortune algorithm, I would also like to show here that this is the seed file. This is the seed file manager. This is the entropy accumulator, and this part is the generator. Fortune is a cryptographically secure algorithm, which means that given the first k bits of a random sequence, there's no polynomial time algorithm that can predict the k plus 1th bit with probability of success greater than 50%. So here, the time complexity doesn't really matter because the output has to be very secure. Now that we've looked at the algorithm, let us take a look at the applications of the algorithm. A practical application of Fortuna is Monte Carlo simulations. And the essential idea of these simulations is to use randomness to solve problems that might be deterministic in principle. So for this, we define a domain of possible inputs, and we generate inputs randomly from a probability distribution over the domain. Also, key generation, nonces, one-time pads, and salts require the cryptographic algorithms to generate a lot of random numbers. So this is where Fortuna comes into play. There have been several loopholes that have been found in cryptographically secure PRNGs. And to keep the loopholes very general, not just limited to Fortuna, we have listed down 3 loopholes, of which I would like to explain one of them, which is the second point. Dual elliptic curve determination random bit generator is a CSPRNG, and it uses elliptical curve cryptography to generate random bits. It was also approved by NIST as a cryptographically secure number generator. But 2 researchers, Dan Schumacher and Niels Ferguson, suggested that the algorithm possibly contained a backdoor which was inserted by National Security Agency, NSA. The algorithm relied on finding a point P on an elliptical curve called a generator, and it used a secret constant Q. There also exists some value E by which Q bar E is equal to P. However, those researchers found an attacker that could compute the initial state of CSPRNG if they found some value such that P bar D is equal to Q. Now, if we know Q and P, then E could be calculated. And then that gives the attacker the access to the initial state as well as a list of future values that CSPRNG would generate. So after these researchers revealed the vulnerability, NIST retracted its approval and warned other developers as well. And then after that, even NSA confirmed that it did indeed hide a backdoor in the algorithm. And this was also revealed by Edward Snowden in the release of NSA classified documents in 2013. So what can we do to prevent such hacks or any kind of a data theft that could be because of a CSPRNG? So one alternative could be to use a TRNG, true random number generators. Avoid deterministic PRNGs altogether. So what is so special about these true random number generators? So these TRNGs, they choose numbers based on external variability, including radioactive decay, atmospheric noise, or even snapshots of lava lamps. Also, they offer a non-deterministic sequence of numbers, which will never repeat at the cost of a difficult setup and inefficiency. They are the best choice, and also the choice of a random number generator depends on the application. As we have discussed the applications previously, we need a random number generator to generate a large number of random numbers every day in our lives for keys, solves, or nonces. And generating good randomness is a vital part for many cryptographic operations. And if an algorithm can generate a large number of random numbers, such that predicting the next random number becomes really hard, then they're called cryptographically secure PRNGs. And they're verified mathematically that they can produce a large number of random numbers. Fortuna happens to be such a such an algorithm. And the measure of randomness is called entropy. So we can say that the entropy for Fortuna is high. CSPRNGs are a vital component in security. They're used by programmers in all fields to build secure systems, to create cryptographic keys, or to encrypt communications, or to defend anonymity. Many are based on deterministic algorithms, and if you break them, that can reveal all the numbers that will be generated, and these will be revealed to the attacker. While many of these number generators have not been compromised, there are some flaws undermining the security. From improper implementation to backdoors, as we saw previously, and entropy collection, the difficulties facing CSPRNGs threaten to crack the foundation of cryptography. While Fortuna might not be the best algorithm to be used if you want a CSPRNG, we have tried our best to highlight how good an algorithm Fortuna can be. So it's very important that when you build an application, you determine how secure you want it to be and what algorithm to go for. While doing this project, we did refer to a few of these resources and they've been quite helpful to understand how Fortuna algorithm works.